All right. Last time we studied about the subspace, and the main requirement for the subspace is that subspace should be closed under linear combination, right? So in order to satisfy this condition, the subspace is literally represented as a span of some finite number of vectors. And those finite number of vectors that are linearly independent and fully span the given subspace is called basis of that subspace. And even for the same subspace, the basis, different versions of a basis may exist, but the number of bases for the given subspace is always the same, right? So that number, or the number of bases, is called the dimension of the subspace, right? And at the end of the last lecture, we studied about this new notion of coordinates of a given vector x relative to the basis b. Okay, so intuitively, the basis vector of a given subspace works as a new axis that defines your new coordinate system. Okay, so in this figure, we discussed a lot about this figure, and so we can imagine this kind of grid formed by the two given bases, for example, V1 and V2, and a particular point in our subspace. So again, we consider the point inside of our subspace, right? So that way, we guarantee that this point is always represented as a linear combination of the given basis vector, right? And the requirement for the basis, one of the requirements of the basis vectors is they are linearly independent, allowing no redundancies, right? So that means it always gives us the unique representation or the single solution, which is in terms of their linear combination coefficient to represent a given point in the subspace, right? And then intuitively, a particular point, for example, like this point, can be viewed as having the coordinate of 2, 3, right? And what is this 2? That is the linear combination coefficient associated with V1, which is the first basis vector. And this 3 is the coordinate, the second dimensional coordinate, and that indicates the linear combination coefficient associated with V2, right? So that's how we consider or define the new coordinate system given a particular basis vectors in a subspace. Okay, and right. So we studied about or we discussed about this example where we are originally given three-dimensional vector in R3, right? But that point is a point inside of our subspace. That has the dimension of 2, right? Which has the two basis vectors, right? And then given a particular basis vector, for example, that if the basis vectors are these guys, and then this 1, 2 is the new representation or the new coordinate relative to the given basis vector. But again, we consider the point inside of our subspace. Okay, so let's think of some similar example where we have we start with an R10, which is really large or high dimensional space, right? And then now we can consider like two basis vector that spans a particular subspace, right? So the first basis vector is 1, 10, 1, 2, 3, and so on, and then maybe 3, 4, 5, and 12. Okay, so that's just an example. So we can think of the subspace spanned by these two linearly independent vectors, right? And then now suppose we pick up or choose any point inside of this subspace. And then we can consider their new coordinate relative to this basis vector, right? And then what is the number of dimensions of this coordinate vector? Or 2, right? Simply the number of, count of these values or numbers, right? So these are, essentially the linear combination coefficient with respect to our given basis, right? So you are effectively convert the 10-dimensional vectors. Originally those points in this subspace spanned by these two basis vectors is actually represented as a 10-dimensional vector, but this 10-dimensional vector is always mapped to particular 2-dimensional vector, or this new coordinate representation relative to the given basis vector. Okay. Okay, so you can think, so this term, I don't even know what it really means, but it at least sounds a little bit complicated. Isomorphism, okay, isomorphism. So isomorphism, the intuitive understanding about it is that, consider a particular dimensional subspace spanned by, for example, in this case, spanned by 2 linearly independent vectors or 2 basis vectors, okay? And then for whatever original dimensional space, okay? And then if that point is chosen from that subspace, and then that point is mapped to always to 2-dimensional vector, similar to this guy. So this guy is mapped to 2-dimensional vector, and this guy has another mapping to, is mapped to another 2-dimensional vector, right? And then these mappings are 1-to-1. And by that I mean you choose a particular point from your subspace, which is originally, for example, 10-dimensional space, okay? And then that will be mapped to a unique 2-dimensional vector. So there is always a unique solution, okay? So you can think of this as, in this case, they are originally living in this 3-dimensional space, but we consider the points inside of our subspace spanned by the 2 linearly independent vectors, okay? And then let's think of so these are really the parallelogram, and so for example, the length is maybe 2, for example, so the length of V1 is 2 and length of V2 is maybe 1, so length is different, and the angle between them may not be a 90-degree angle, right? So they can have some arbitrary angle, right? But how about this 1, 2? Let's just view this 1, 2 as the typical or standard coordinate in this regular grid type of 2-dimensional vector, x and y, or x1 or x2, or v1 and v2, and so on. And here we always assume that, so what's the meaning of having the point of the coordinate of 1, 2, 1, 2 over here, and 5, 1, 5, 1 is over here, right? So in this case, the linear combination coefficient, or 2, 1, 1, 2 is equivalent to having the basis or using the basis as a standard basis vector of 1, 0 and 0, 1 in R2, 2-dimensional vector. So this guy is 1, 0, and this guy is 0, 1, right? So this first axis, is mapped to this guy, 1, 0, and the second axis, which is our V2, which is this guy, okay? That guy is mapped to 0, 1, Okay, and then this 1 comma 2 is mapped over here, and 5 comma 1 is mapped over here. So you choose any point from your subspace, for example, like this point. Okay, so this point has the coordinate of 1 comma 3 with respect to v1 and v2. But if we convert v1 and v2 as this standard basis in just a two-dimensional space, okay, as a in other words, 1 0 and 0 1 are our new basis in just a two-dimensional space. Okay, and in that case, this point 1 comma 2, 1 comma 3 is mapped over here, and 1 comma 2 is mapped over here, and this guy 2 comma 2 is mapped over here, and 3 comma 1 is mapped over here, and so on, right? So the main point is that this guy, this subspace, the blue colored plane, and a particular point in that blue plane is mapped to a unique point in just a two-dimensional space. Okay, so there is in one-to-one correspondences or one-to-one mapping. So that is the meaning of isomorphism. Okay, so you can so I'll discuss more about this isomorphism in order to explain some other relations. Okay. So in this definition, we already discussed the definition of dimension. Simply, the dimension is the number of basis vector of a given subspace, and as I mentioned, the dimension is unique for a given particular subspace, although the basis vectors may vary or may be different, right? And then let's think of some special case of zero subspace, which contains only the origin. Okay, so for example, 0 0 0, and that's it. So it's of course some subset of the vectors in R3, and is this subspace or not? In other words, does it satisfy like closeness under the linear combinations? Yes, it is, right? And so it is a valid subspace. But what about their basis? So in this case, you can think of the basis as like 0 0 0, for example, because we at least see one vector as origin or 0, and so it's tempting to include it in our basis vector set. But 0 vector itself is already a linearly independent set. Linearly dependent set, because 0 0 0 and maybe C1 plus nothing, right? Because we have only one vector. And then let's think of like this homogeneous linear system and check whether we have non-trivial solutions, right? We have, right? So if we set it as maybe 3 or 4 or 5, and then it still satisfies this equation, so it is the solution for this homogeneous linear system with the non-zero element, which corresponds to non-trivial solution. And thus this zero vector only, I mean it's a single vector composed of this zero vector, this guy is linearly dependent. So we can view or consider the zero subspace has no basis, because the requirement, one of the requirements for the basis is that they should be linearly independent. Right, and then also we studied about the definition of the rank. So simply, so column space of A, their notation is written in here, and then dimension of the column space is written over here, and then that is the rank of A. And then simply the rank of an A and the dimension of the column space, we will see the example over here. So determine the rank of this given matrix, and then once we perform the Gaussian elimination, so this seems to be the echelon form, but not reduced echelon form. But at least we can identify which are the basic variables and which others are free variables. So B, F, F, B, F, right? So the dimension of the column space is PB. Oh, right, right. Yeah, thanks. So here, the dimension of the column space is 3, right? And the rank of this matrix is also 3. And then if we are asked to give a basis of the column space, then this guy and this guy and this guy, right? So the set of these 3 vectors is the basis of the column space of this matrix. Okay. And so yeah, we also discussed about this rank theorem. And then now let's look at the next theorem called the basis theorem. Okay, basis theorem. So yeah, let me first explain what this basis theorem says. So the starting point or the initial situation is that we are given a particular subspace, and someone told us the dimension of the subspace is, for example, 3. Okay, so given a subspace, and it can be maybe R10 or maybe R15 or R even 100 and so on, but at least someone told that the dimension of this subspace is 3. Okay, and that means the number of basis vectors that are linearly independent and fully spans the subspace is 3, right? And then we want suppose we want to find out a particular basis vectors. I mean, it can be whatever basis vectors that satisfies this condition or requirement of a basis vectors. But to achieve this goal, we have to consider 2 conditions of basis vectors. The first one is fully spanning the given subspace, and the other one is the vectors are linearly independent, right? So we have 2 conditions that have to be satisfied simultaneously, right? But the point of this basis theorem is that so you already know the dimension of this subspace, and then suppose you found out 3 linearly independent vectors inside of this subspace. Okay, and then will these 3 vectors basis of this subspace? We do not know yet, because we do not know whether they are fully spanning the given subspace, right? We only know the 3 vectors are linearly independent. Okay, and again we know that the dimension of the subspace is 3. Okay, so that is the given kind of information beforehand. And in this case, the main point of this theorem is that so if we found 3 linearly independent vectors, okay, then they automatically fully span our subspace, and thus they are basis of this subspace. And on the other hand, so here the point is that we have 2 conditions to satisfy for the basis vector. But if we found the 3 linearly independent vectors, and then they are automatically fully spanning the subspace. Okay, and then also suppose you found 3 vectors that fully spans the subspace. Okay, and then they are automatically linearly independent. Okay, so even though we have 2 different conditions to satisfy, but if we found this 3, which is the same number the same number of vectors with the given dimensions of this subspace. Okay, and then if those vectors are satisfying either of these 2 conditions, and then these vectors will satisfy the other conditions just automatically. Okay, so let me just describe it a little bit more by using this example. All right, so suppose we are given this plane, okay, without being given any particular basis vectors of v1 and v2 and so on. Okay, but we at least know, so this is an initial assumption that, or the initial information to start with, and someone, when giving this basis to us, that guy told us that this subspace, when someone gave this subspace, and then that guy also told that, okay, the dimension of this subspace is 2. Okay, so that is the initial situation to start with. And here, from the subspace, you choose the 2 vectors that are linearly independent. Okay, and then that will automatically fully span your subspace. And also, if you found just the 2 vectors that fully spans the subspace, and then they are automatically linearly independent. Okay, so that is the point. And in order to understand, or at least to prove it informally, we need this kind of isomorphism. And also, we will utilize this invariability. What was that? Yeah, invariable matrix theorem, which had a lot of different items or conditions that are equivalent to each other. So, what was the invariable matrix theorem? So there were a lot, right? So let's remind ourselves. Where was it? It was in the 2.3. Like this guy, right? So invariable matrix theorem. So there were a lot of different conditions when that invariable matrix will satisfy. But here, what was the main point? There were many kind of insights from this theorem, but in my opinion, one of the most important insights that we can have from this theorem is that, so in order to discuss whether a given matrix is invariable or not, we consider the square matrix. Okay, the square matrix, and in that square matrix, we consider where the pivots are, right? And from the columns perspective, the row perspective, and the column perspective. So if the pivots are found in every row in the square matrix, right? And then what does that mean? It means, it will guarantee the solution. It will guarantee the existence of a solution for whatever b vector is, for the ax is equal to b, right? And then also another kind of interpretation of it is the column space of this matrix will fully span the entire Rn, right? So that was the meaning or the characteristic of having the pivot in every row, right? And then the main point of this theorem is that, okay, so given a square matrix, if we have a pivot in every row, and then it means simply we have a pivot in every column, right? So what does that mean? So it also implies, or it also will lead us to linear independence of the columns, right? And also the unique solution, okay? So it does not only just guarantee the existence of solution, and also at the same time, it will also guarantee the uniqueness of the solution all the time, right? So both of them will happen simultaneously, or both of them will not happen. For any of them, right? So, simply having the pivots in every row will be equivalent to having the pivots in every column, and vice versa. In other words, if we have a pivot in every column, and then it means we will have a pivot in every row as well, right? So that was due to the simple kind of shape of the square matrix of having the same number of rows and same number of columns, right? Okay, so that is the point of this invariable matrix theorem. Okay, so let's see how this insight is related to this basis theorem that we are discussing. So here, so given this figure, okay, so again, this basis theorem is saying that, okay, suppose we found 2 vectors that are linearly independent. Okay, and then what does that mean? It fully spans this subspace, right? Right? And so suppose you found such two vectors that are linearly independent. For example, like this guy and this guy. Okay? And finding out these two linearly independent vectors will be equivalent to finding out, yeah, this guy is corresponding to some vector over here in just a two-dimensional space where our coordinate system is based on this regular grid or the standard basis vector. Okay, and the second one, okay, second one that we found over here will be mapped to a particular point, right? So due to this one-to-one mapping, finding out, choosing some vectors from here that are originally represented in this three-dimensional space, right? And that is equivalent to choosing the same number of vectors in this two-dimensional vectors. Okay, so if this guy, if this guy was like, this guy 5, 8, 11, and then that will be mapped to a unique point or somewhere over here. Okay, so finding out or choosing the two vectors over here originally in the three-dimensional space or maybe 10-dimensional space or whatever dimensional space originally, and that will be equivalent to choosing those vectors in this two-dimensional space. So here, where is this number coming from? This is the number of bases of this subspace, right? Okay, so so now it's like, it's equivalent to choosing the two vectors that are linearly independent in two-dimensional space. Okay, and again, two vectors in two-dimensional space. What does that mean? If we collect those columns as a column of our matrix, and then that matrix will be just a square matrix. Okay, square matrix. Okay, so what's the meaning of linearly independent vectors over here? So that is equivalent to the fact that those two corresponding vectors are linearly independent in just a two-dimensional space, right? And then due to this, based on this invariability or inverse matrix theorem, and then those two vectors, okay, this matrix, those two vectors will fully span R2, right? R2. What does that mean? Using those two vectors that are linearly independent, and then we can, by spanning them, we can entirely cover up this entire two-dimensional space. So what does that mean? What does it mean by covering entirely the two-dimensional space up? So that is covering entirely this given subspace, because we have always this one-to-one correspondences or one-to-one mapping between the points over here and points over here. Okay, does it make sense? And also, in other situations, in the opposite situations, suppose you found the two vectors that fully spans the given subspace, and it would mean that those two chosen vectors will fully span this two-dimensional space R2, right? And then it means that we chose two vectors in two-dimensional space, and then those two columns are spanning the R2. What does that mean? The pivots are existing in every row in this matrix. And what does that mean? Because of the shape of this matrix, which is a square matrix, okay? The same number of vectors in the same number of dimensions, right? So these two vectors should be linearly independent, okay? So we can kind of understand why this basis theorem should be true based on this invariability I mean inverse matrix theorem. Any questions? 네.
In slide 6, the coordinate vectors belong to R2.
In this slide?
Yes.
In which line?
In the third line.
Third line, okay.
Coordinate vectors belong to R3.
Right.
It should belong to R2, right?
Right. So this is kind of main point. So in this case, so the reason why I mentioned that okay, so we are starting with, or we initially handle the vectors, or we initially consider the vectors in whatever dimensional space, which is like 10-dimensional space or 100-dimensional space, or in this case 3-dimensional space originally. But when talking about a particular subspace, okay, and that subspace dimension is 2, okay, and then due to this thing, okay, due to this thing, so much higher dimensional vector representation is actually mapped, like based on 1-to-1 mapping, is actually mapped to much lower dimensional vector or point. And what is the lower dimensional space and its dimension? And that dimension is the actual number of bases or dimension of the subspace. So the subspace is 2-dimensional, or it has the dimension of 2, or the number of bases of the subspace is 2, right? And then in that case, even if the subspace is embedded, or this subspace is belonging to much higher dimensional space, but if we just extract out, or we just crop them out carefully, and then we just bring it and then just attach it to this regular grid system in just a 2-dimensional space, okay, or whatever actual number of dimensional space where that dimension is the dimension of our subspace, okay. So in this example, even though all these points inside of the subspace are initially represented as the 3-dimensional space, but it's like handling them, or considering their actual 2-dimensional representations, and then we can understand this basis theorem in this 2-dimensional space. Any other questions? Right, and then as we saw in this, see, so a lot of lists included in our basis theorem. Invertible matrix theorem, and then now we have a set of additional items or statements that should be included in our invertible matrix theorem. So when the matrix is invertible, so again we are considering the square matrix, and then these are just there is actually no new concepts or new additional stuffs to understand, but it's involving or utilizing the new notions that we studied related to this topic of a subspace. So the columns of an A forms the basis of an Rn, right? So what does that mean? The span of the columns is Rn, right? And what does that mean? I mean, the columns are linearly independent, and they are fully spanning the Rn, right? And so when this condition is satisfied, the matrix will be invertible, right? And so here, the basis again should satisfy the two conditions, right? But this is a square matrix, so we don't actually need the two conditions separately. So if we just satisfy one conditions, or linear independence among those columns, or the fully spanning the Rn, okay, if we satisfy only one of the conditions and then the other one is just automatically satisfied, and thus they work as the basis for our subspace. What is our subspace over here? Subspace is Rn, the entire n-dimensional space. And also the column space will fully span Rn, so that is the same thing. And then the dimension of the column space of an A is n, right? So like in three-dimensional vectors, then we think of like three vectors in the three-dimensional space, right? So in this case, if they are linearly independent, and then what is the dimension of the column space or the rank of the matrix? It will be 3, right? And then what about the null space? So from the rank theorem, what was the rank theorem? So dimension of the column space of an A plus dimension of the null space of an A should be n, where it is 3, right? So this is already is 3 and this is 0, right? So what does that mean? So we have only the trivial solution for the homogeneous linear system. Right? So I think you can easily understand these additional kind of items or statements to add to our invertible matrix theorem. Okay, so we already have A to the R different statements that are equivalent to the invertibility of our matrix. And this is not the end, so you will add a little bit more in the later chapters. Okay, any questions so far? Right? Then let's say for the big chapter 2, and then the chapter 3. The big chapter 3 is about the determinant, and we will completely skip that part or that chapter. But yeah, please note that this chapter is like a chapter for your self-study. Okay, but you actually don't need to follow the book, so you actually have to study like 2.5 hour long video lectures, okay, given by the famous professor at the MIT, and that is one of your homework that was already posted or announced last night. And yeah, please be prepared for the quiz next Wednesday. So you have to watch it and understand it before next Wednesday's class, and we will have a brief quiz in the beginning of our class. Okay, and that lecture is really, hopefully it's a really fun one. It's really fun to study. I personally think it's a really beautiful lectures. It starts with the two simple kind of conditions of the determinant of a matrix to satisfy, and then it expands to a lot more more number of lists, which will give us much more interesting characteristic of a matrix. So yeah, I remember that you guys didn't study about the definition of the determinant of like AD minus BC. You haven't studied it in your high school? 네? 역행렬 맞아요 그게 그거예요. 네.
고등학교 때 알았어요.
네, 판별식이. 그러니까 그럼 어떻게 알아요 이건? 수업? 어느 수업? 아, 우리 수업? 우리 수업. 네, 오케이. 네, 맞아요. 역행렬. 그렇죠. 네. 역행렬 때 나오는 그 분모에 들어가는. So this this number is placed in the denominator when forming or when computing the inverse matrix, at least for this 2x2 matrix. And this determinant has an interesting characteristic. Intuitive meaning of this determinant of a given matrix is that, if it is 0, and then it means your matrix doesn't have an inverse matrix. It is not invertible. Okay, and if it is not 0, and then it is invertible. Okay, so at least you have an you can easily add another condition over here. The determinant of a matrix A is not 0. Okay, so that is an equivalent or necessary and sufficient condition for a matrix to be invariable. Okay, and also, although that lecture will not cover this additional interesting stuff, but when it is non-zero, okay, then AD minus, suppose AD minus BC is maybe 5 or maybe 10. Both of them are non-zero one. So it will indicate that this matrix is invariable, right? But is there any kind of physical meanings of the value itself? Okay, value itself. This value is, has some interesting meaning of like the ratio of an volume expansion. So it's like, so I mean, it's a little bit off topic, so you can, it's completely okay, even if you don't understand it. I mean, it's just for your information. But in the two-dimensional space, let's think of this guy. Okay, it's a 1, 0, and 0, 1, and 1, 1. And then what's the volume or area of it, or area of the square? It is 1, right? This is 1, and this is 1, and 1 times 1 is 1, right? And then suppose you have like 1, 2, 3, 4. Okay, so what is AD minus BC? 4 minus 6, right? It's negative 2, right? And then this negative 2, let me just change it as 5, and then it's a 14, right? I mean, you actually have to make it as an absolute value. So in this case, it is 2, and it is 14, right? And then this number is basically the expansion ratio of your unit rectangle or whatever unit kind of shape of a polygon. So here, 1, 0 is linearly transformed into what? 5, 3, and 2, 4, right? And then what about this guy? So 5, 3, no, 5, 3, 2, 4, and then what about this guy? It will be like this guy, right? So this point is mapped to here, this point is mapped to here, this point is mapped over here, right? And then what will be the ratio? I mean the area of this parallelogram. This parallelogram is, in case of this guy, it will be 14, right? So let's imagine some other arbitrary shape, like this kind of shape. And then you just map all these points through this mapping, okay? And then we will have some, corresponding shape. And then the area or the volume inside of this points, will be expanded by the ratio 14. So that is the physical meaning of this determinant, but this is completely out of topic, especially for the undergrad level linear algebra. Okay, so again, chapter 3 is your the topics for your self-study. That should be done before the next Wednesday, and then we will have a brief quiz. So please study them carefully. And then we now jump to the new big chapter of chapter 6. Okay. So for chapter 4, it's we will not cover it at all in our class. And chapter 4, chapter 4 is quite highly overlapping with what we studied in chapter 2, including subspace and so on. So I don't know about how this book was organized, but anyways, chapter 4, you don't need to, you completely skip the chapter 4. Although chapter 3 about the determinant, although we do not cover it in our class, but you have to study them, and then also you will see the homeworks from this chapter 3, and based on what you study from these two, the video or online lectures, you should be able to handle, or you should be able to solve all these exercise problems from chapter 3 with no problem. Okay. And then also about chapter 5. Yeah, we will cover chapter 5. So that is really important part. Okay. But yeah, somehow, yeah, we will study first chapter 6, and chapter 5 and 6 is completely independent. Okay, so chapter 6 is about the orthogonality. So orthogonality is like being perpendicular. Okay, perpendicular. What's the meaning of the being perpendicular? Given the two lines, the angle is 90 degree. 네, 수직이라는 뜻이죠, 수직. So yeah, it's a more kind of mathematical version of the words. Is this orthogonal and orthogonality? And then here we consider another important operation between the two vectors called the inner product. So given the two same dimensional vectors in Rn commonly, and then we consider their column vectors, right? And then if we view it as a matrix, and then it is viewed as a n by 1 matrices, and then the inner product, or it is also called the dot product, because the operator is really written as dot. Okay, so the dot product is defined as like, so let me give an example. So let's consider R3 and 1, 2, 3, and dot product of 4, 5, 6. Okay, so the dot product between the two vectors is so it is n by 1 matrix. We can view each of these two column vectors as n by 1 matrix or 3 by 1 matrix, right? And we already know the matrix multiplication, and then this dot product or inner product is defined as matrix multiplication, where the first vector is transposed 1, 2, 3, and 4, 5, 6. Okay, so this is again a matrix multiplication where we don't have any special operators over here, right? And then here it is a 1 by 3 and 3 by 1 matrix, and so it will produce 1 by 1 matrix, which is just a scalar, right? And then you can easily compute it. 1 by 4, 1 times 4, 2 times 5, 3 times 6, and then sum them up, right? So this result is called inner product. We already studied it, right? When discussing the matrix multiplication. And this inner product has these interesting properties. Hopefully interesting properties, satisfying this commutative law, right? When changing the order between them to perform these operations on, the result will be the same. So this is a distributive law, and this is a kind of an associative law where C is scalar multiple. Okay, so you first scalar multiple with some vector, and then perform the inner product. That will be the same as just first performing the inner product and multiplying that scalar later on. Okay, and then let me discuss this finally. So this guy, we can think of this the inner product with the same thing, okay, same vector. So for example, 3, 4, which is two-dimensional vector, and the two-dimensional vector, and then what is it? 3, 4, 3, 4, and 3 squared and 4 squared, which is the sum of the same value, the square root of the each dimensional value, right? So the sum of squared values will always be positive or 0. I mean, it will be at least non-negative, right? And when is it exactly 0? This is only achieved when your vector is 0 vector or origin, right? Okay, and then also lastly, this guy is like combining those two, B and C, and then we can easily combine, obtain the last one. And the last one, the meaning of the last one. So meaning of the last one is that this inner product is kind of linear transformation, which means So you performing the inner product with this and this, which is the linear combination of some vectors first, and then performing the inner product, and that will be the same as inner product first, and then later on we combine them using this linear combination coefficient, and then those results will be the same. Okay, so we will utilize these when proving or deriving some more interesting stuffs later on. Okay, that's it for today. And so yeah, please note that we have two homeworks of watching video lectures and another one of solving this chapter 2 exercise. Thanks.
질문 있었는데
네.
혹시 A의 랭크가 A의 파이버수와 같다는 걸 증명 한 번만 더 보여주실 수 있어요?
랭크가 이제 피벗수랑 같다는 거요?
네네.
그러니까 랭크는 이제 디멘전의 컬럼 스페이스의 디멘전이 맞고요. 그 다음에 이게 네, 그러니까 이게 결국은 뭐 이렇게 이게 피벗 컬럼이 이제 베이직 베리어블에 해당이 되는 거고요. 그 다음에 얘네 그러니까 이게 컬럼 스페이스라는 거는 이것들을 하나씩 우리가 추가를 해서 스팬을 더 늘려가는 어떤 시나리오를 생각을 해보면 그러면 이제 얘가 추가가 됐으면 늘어났고요. 얘는 근데 그러니까 우리는 베이시스 어떤 서브스페이스의 베이시스를 생각을 하려면 걔네들 리니얼 인디펜던트 해야 되는데 얘는 지금 이 두 번째 컬럼은 이거에 이제 스케일러 멀티플로 표현이 되는 거잖아요. 네, 그러니까 이제 이거는 우리의 스팬을 늘려주지 못하고 그 말은 또 이제 다시 말하면 이거는 이제 그 전 벡터들의 리니어 콤비네이션 혹은 그 전 벡터들의 스팬 안에 포함이 된다는 뜻이잖아요. 그러니까 얘는 이제 리니얼리 디펜던트 하니까 얘는 빠져야 되고요.
그래서 파이버만 남아.
네, 맞아요.
네, 감사합니다.
네. 네.
P 디멘셔널 스페이스 서브스페이스에서
네.
이 두 개가 그 벡터들이 베이시스인 조건 두 가지가 있는데
네.
그게 디펜던트랑 풀리 스팬인데 이게 서로 네, if and only if라는 거죠. 그래서
네.
하나만 찾으면
맞아요. 근데 여기서 조건은 지금 여기서 봤듯이 지금 우리의 서브스페이스의 디멘전이 P라고 주어져 있고요.
네.
우리가 P개의 리니얼리 인디펜던트한 벡터를 찾았을 때 그 P개의 벡터는 풀리 스팬을 한다는 거고
네.
혹은 P개의 이 풀리 스팬, 이 서브스페이스 풀리 스팬 하는 걸 찾으면 얘네들은 이제 리니얼리 인디펜던트 색이라는 뜻이 되거든요.
네.
네.
네. 그리고 이게 제가 이 설명을 잘 못했는데 이게 지금 스퀘어 맷 뭘 증명하려고 한 건지
네, 이게 조금 뭐 설명이 좀 약간 난해했을 수 있는데, 그러니까 여기서 예를 들면 두 개 리니얼리 인디펜던트한 걸 찾았어요.
네.
근데 걔네들이 이 서브스페이스를 풀리 스팬하는지는 사실 이거는 쉽게 증명이 되지는 않아요.
네.
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 근데 그거를 좀 증명을 뭐 하기 위해서는 그러니까 결국은 여기서의 3차원에 존재하긴 하지만 어쨌건 이 서브스페이스에 있는 어떤 포인트 두 개를 골랐으면
네.
그거는 뭔가 하여튼 이런 어떤 주어진 베이시스에 대한 어떤 두 개의 숫자로 이루어지는 코오디네이트로 나타내질 거고요.
네.
혹은 이 베이시스 두 개의 벡터의
네.
리니어 콤비네이션으로 나타내질 것이고
네.
그러면 그 말은 아까 얘기한 게 이제 뭐냐면 이제 이게
네.
이런 3차원 벡터가 있으면 걔는 어쨌건 뭔가 2디멘셔널 스페이스의 어떤 포인트, 그러니까 이거는 이 B라는 베이시스를 썼을 때의 어떤 코오디네이트 혹은 그 코에피션트긴 하지만 결국 이 숫자 자체만 본다면 그냥 이 XY 축으로 이루어진 2차원에서 잠깐만요. 그 2차원에서 교수님 금방 제가 하겠습니다. 그 2차원에 있는 어떤 포인트에 대응이 된다는 거죠. 그러니까 그게 1대1로 대응이 된다는 거고요. 그 1대1로 대응이 되니까 결국은 그 3차원에 있는 포인트들을 우리가 그 3차원에 있는 포인트 그냥 그거를 고지고대를 생각하지 않고 그거를 그냥 2차원에 있는 어떤 포인트로 만약에 다 컨버트해서 생각을 하면 그러면 결국 우리가 P개의 벡터를 P개의 디멘셔널 스페이스에서 찾은 것과 같아요. 그러면은 그 컬럼이 결국은 그러니까 지금 얘기했던 것처럼 P 디멘셔널 스페이스에서의 P개의 컬럼, 즉 이제 스퀘어 매트릭스를 만들게 되니까 지금 거기서 이제 우리가 인버터빌리티 혹은 인버스 매트릭스 티어럼 같은 걸 쓸 수 있다는 거죠.